We are now going to take up a class of problems where we are given a large collection of sets, millions or billions perhaps, and we are asked to find those sets that are similar. The notion of similarity is quite specific, and it's called Jacquard similarity. We'll learn this concept soon, but the idea is roughly that the larger the fraction of elements that the two sets have in common, the more similar they are. There is a fundamental problem of scale. If we have even 1 million sets, not a large number compared with the number of web pages or Amazon users, the number of pairs of sets is 500 billion. We don't have the resources to compare them all, so we need some magic to focus us on the pairs that are likely to be highly similar, never looking at the vast majority of pairs. When you learned about hashing, it probably seemed like a bit of magic. You have a large set of keys, and when you want to find some key K, you go right to it without having to look very far at all. The technique we're going to learn, locality-sensitive hashing, is another bit of magic. Here we are pointed right at the similar pairs without having to wade through the morass of all pairs. We'll begin by looking at some applications where finding similar sets is very useful. We then are going to focus initially on finding similar documents, meaning that they have a substantial amount of text in common. For this problem, we first study shingling, which is a way to convert the informal notion of similar documents into a formal test for similarity of sets. Then we learn the remarkable technique called min-hashing, which allows us to replace a large set by a much smaller list of values. The magic of min-hashing is that the similarity of the small lists, called signatures, predicts the similarity of the whole sets. Finally, we take up the locality-sensitive hashing technique itself and see how to find similar sets or similar documents without doing anything that involves searching all pairs. To begin, let's look at some of the interesting data mining problems that fit the pattern of mining for similar sets. For example, we can view web pages as the set of words they contain. If two pages have similar sets of words, we might expect them to be about the same topic. For another example, imagine a matrix of Netflix users where the rows correspond to the users and the columns to the movies. The entry for a given user and movie is the rating that the user has given the movie, blank, if no rating. We might see a user as the set of movies they have rated 4 or 5, that is, movies they like. Two users who have similar sets of liked movies probably have the same tastes, and Netflix can use the movies one user said they liked to recommend movies to the other. We can use the same idea backwards, where we think of a movie as the set of users who liked that movie. Movies with similar sets of users can be expected to belong to the same genre of movie. People create records of data about themselves at many different sites, Google, Amazon, Facebook, and so on. We may want to figure out when two records refer to the same individual, and this need gives rise to the problem called entity resolution, determining the set of records that refer to the same individual. To see the problem, many sites will ask for a phone number, but you might give your landline at one site, your cell phone number at another, not give a number at all at a third site, and mistype your number at a fourth. However, we can often wade through the errors and ambiguities by thinking of a record as a set of attribute value pairs. Pairs like phone is 555, whatever. Okay. Records with similar, even if not identical, sets of attribute value pairs may well represent the same individual, and these records can be merged to combine their information. We're going to focus on a particular important application, finding lexically similar documents in a large collection of docs, such as the web. Note, we are not talking about docs on a similar topic. We want them to have sequences of characters in common. This question has a variety of applications. For example, the techniques we're going to learn were used to find mirror pages on the web. Mirror pages are typically almost the same, but they will differ, for example, in the information about the host site for the page and links to the other mirrors. Search engines use a technique like the one we'll learn, so they don't show more than one of a set of mirror sites. Another application of finding lexically similar documents is to search for plagiarisms. For example, spammers will take your web page, give it a new URL, and place ads around it. The plagiarizer may be clever, taking only a part of the plagiarized document, reordering pieces, perhaps changing a word here and there. We still want to be able to find such pairs of documents in a collection as large as the web without having to compare all pairs of documents. It can be done. In fact, it's much easier than it looks. And another application concerns sites like Google News that aggregate news stories. An article may be written by the Associated Press and distributed to thousands of newspapers and online news sites. Each will make modifications, perhaps truncating the story, surrounding it with ads, and so on. It's important for an aggregator to realize that the two web pages are really telling the same story because they came from the same original, even if they have been significantly modified. As we suggested in the introduction, we're going to learn three important new techniques. Shingling is how we convert documents to sets so that documents that have a lot of text in common will be converted to sets that are similar in the sense that they have a lot of members in common. Then we'll learn about min-hashing, which is how we convert sets to short signatures. The important property is that we can look at the signatures of two sets and tell approximately how similar are the sets that we obtained by the shingling process. And last but not least, we'll learn the technique called locality-sensitive hashing, or LSH, that lets us avoid looking at most of the pairs of signatures that do not represent similar sets. Here's an outline of how we process documents to find those that are similar without comparing all pairs. At the outset, I want to emphasize that there can be both false positives and false negatives. That is, the algorithms we use can sometimes fail to find a pair of documents that we would regard as similar. That's a false negative. We can also, if we're not careful to check the details of the document, sometimes have false positives, pairs of documents we declare to be similar, but they really aren't. However, by carefully choosing the parameters involved, we can make the probability of false positives and negatives be as small as we like. So we start by shingling the document. That is, we replace the document by the set of strings of some chosen length k that appear in the document. That's how we convert documents to sets. We then construct signatures for the sets of shingles using the technique called min-hashing. The result of min-hashing a set is a short vector of integers. The key property, which we'll prove, is that the number of components in which the two of these vectors agree is the expected value of the similarity of the underlying sets. Incidentally, the reason we want to replace sets by their signatures is that the signatures take up much less space. If we're dealing with a large set of documents, we'd like to be able to work in main memory rather than with disk for efficiency, and reducing the space of the representations makes it more likely that we can work in main memory. But it seems we still need to compare all pairs of signatures, and that takes time that is quadratic in the number of documents. As we mentioned, even 1 million documents leads to 500 billion pairs of signatures to compare, and that is too much. So that's where locality-sensitive hashing comes in. We do some magic, which we'll explain soon, that allows us to look at a small subset of the possible pairs and test only those pairs for similarity. By doing so, we get almost all the pairs that are truly similar, and the total time spent is much less than quadratic. So let's begin the story by defining exactly what shingles are. For any integer k, a k-shingle, or sometimes called a k-gram, is a sequence of k consecutive characters in the document. The blanks that separate the words of the document are normally considered characters. If the document involves tags, such as an HTML document, then the tags may also be considered characters, or they could be ignored. So here's an example of a little document consisting of the 5 characters ABCAB. We'll use k equals 2 for this little example, although in practice you want to use a k that is large enough that most sequences of k characters do not appear in the document. A k in the range 5 to 10 is generally used, but the 2 shingles for our little document are AB, is that, then BC, then CA, and then AB again. Since we're constructing a set, we include the repeated two-shingle AB only once. And thus, our document ABCAB is represented by the set of shingles AB, BC, and CA. We need to assure ourselves that replacing a document by its shingles still lets us detect pairs of documents that are intuitively similar. In fact, similarity of shingle sets captures many of the kinds of document changes that we would regard as keeping the document similar. For example, if we're using K-shingles and we change one word, only the K-shingles to the left and right of the word, as well as shingles within the word, can be affected. And we can reorder entire paragraphs without affecting any shingles except the shingles that cross the boundaries between the paragraph removed and the paragraphs just before and after in both the new and old positions. For example, suppose we use K equals 3 and we correctly change the which in the sentence to that. The only shingles that can be affected are the ones that begin at most 2 characters before which and end at most 2 characters after which. Okay, these are G blank W, blank WH, and so on up to H blank C, a total of 7 shingles. These are replaced by 6 different shingles, G blank T, T blank TH, and so on up to T blank C. However, all shingles other than these remain the same in the 2 sentences. Because documents tend to consist mostly of the 26 letters, and we want to make sure that most shingles do not appear in a document, we are often forced to use a large value of K, like K equals 10, but the number of different strings of length 10 that will actually appear in any document is much smaller than 256 to the 10th power, or even 26 to the 10th power. Thus, it is common to compress shingles to save space while still preserving the property that most shingles do not appear in a given document. For example, we can hash strings of length 10 to 32 bits or 4 bytes, thus saving 60% of the space that are needed to store the shingle sets. The result of hashing shingles is often called a token. Thus, we can construct for a document the set of its tokens. We construct a shingle set and then hash each shingle to get a token. Since documents are much shorter than 2 to the 32nd power bytes, we still can be sure that a document has only a small fraction of the possible tokens in its sets. There's a small chance of a collision where 2 shingles hash to the same token, but that could make 2 documents appear to have shingles in common when in fact they have different shingles. But such an occurrence will be quite rare. In what follows, we'll continue to refer to shingle sets when these sets might consist of tokens rather than the raw shingles.